All right, so bottom line with chain rule is if I am composing two functions, this is really what you want to think about. If I'm calling y f of g of x, this is what you want to take away from this. Then the derivative of this, right, then dy over dx is equal to, now think about this, I am composing, this is what I'm going to call, it's going to drive you guys nuts, but this, what just happened there, this is what I'm going to call my blah. It's f of blah, right? So the derivative of this is simply f primed of blah, which is f primed of g of x. But then we have to take into account g of x's derivative. So it's g primed of x. Now, what if I have y equals f of g of h of x? Now, don't be intimidated. It looks contrived, but it's really not. For example, what if I have f of x equals the sine of the square root of x to the fourth plus 3x plus 1, just for giggles, right? Now let's look at what happens. So first things first, I'm going to use some colors on this, and then we'll actually put this into practice. I'm going to call this blah. It's just f of blah. The trick is just to simplify it in your brain as much as you possibly can. Okay, so when I take the derivative, I get f primed of blah, which is just f primed of g of h of x. However, I then have to take the derivative of the blah, and it in itself has this little composition in it. This h of x is being composed into g. So you guys are going to hate me for this, but I'm going to call this blee. Don't make me do a third one because I'll call it blue. Oh wait, maybe I will call it blue. All right. So what do? I take the derivative of the blah, so it's times g primed of h of x. All right? And then I have to take the derivative of the blue, that thing that was being composed in there. So this is just times, let's change colors. This is just times h primed of x. Now, students, especially when journeyman students, when they're first starting out with this, because it can be really confusing, what they'll do is they'll take too many derivatives, or they won't take enough derivatives. So the trick is to look at how many compositions you're looking at. So if I look at this thing, let's look at this guy right here. I'm looking at sine of something. But the problem is that something is a square root of something. So let me show you what I mean here. I could call h of x, in this case, x to the fourth plus 3x plus, I think that was supposed to be a 1, and I forgot to write it. If not, no big deal. Now, that's being composed into a square root function. So I could call g of x the square root of x, because this guy ends up getting stuck in here. And then all of this mess, this whole chunk right here, gets composed into, let's call this, ooh, I don't like my notation. You know what? I'm going to call that, because I got an f of x over here. So let's simplify the process and call this a y. Because otherwise I'm calling an f of x something which it isn't, and Ripley screams and yells when that happens. So sine of x. So really, at its simplest, this is f of g of h of x. You see it? This guy goes in here, this guy goes in here. There are three functions that are being combined at once. So when I take the derivative, I have to take the derivative of three functions. Now, y prime, let's make sure. I'm going to beat on you, and I already have beat on you about functions that you have to memorize the derivatives of. One is sine. So the derivative of sine of blah is the cosine of blah. So this is the square root of x to the fourth plus 3x plus 1. Now I'm going to take the derivative of the square root, which I've told you, you have to memorize it. It's got to be on the hard drive. You have to not think about it. So the square root of blee, or blue, the square root of blue, the derivative of the square root of anything is 1 over 2 times the square root of that anything, right? And then, because this guy right here is the last thing that we composed, we take the derivative of that, and I get 4x cubed plus 3. Okay? And this, as nasty as it looks, is just the derivative of this. I took 1, 2, 3 derivatives because I composed 1, 2, 3 functions. Now, don't disregard all your other rules. Let me give you an example. What if I let y, you're going to hate me for this, but that's all right. I'm used to it. What if I take y equals e to the x plus 1 divided by x minus 1? All right, so again, I'm thinking about this as e to the blah in my brain. Well, I like that. That's easy because y prime equals e to the blah, right? The derivative of e to the anything is e to that anything. But the problem is, you ready? This is where you start not liking me as much. The problem with this is when I take the derivative of the blah, I have to use quotient rule. It's a quotient. Now, it's not a composition. Nothing's being composed here. I guess you can make it a composition, but you make it far too complicated. It's a simple quotient rule, right, which is low d high, so x minus 1 times the derivative of the top minus high, x plus 1, times the derivative of the bottom. I didn't make it too bad, did I? All over low squared. So x minus 1 squared. Now, this one's worth cleaning up just a little bit. This is going to be e to the x. Oh, by the way, I should probably put this in parentheses so that I realize I want to be algebraically accurate. So e to the x plus 1 over x minus 1 times. Now, this, what's this thing simplified to? X minus 1 minus x minus 1 over x minus 1 squared. Now, remember, I said do algebra as long as it's easy. You always want to take it one algebraic step further, but this one's obvious to see that my x's cancel, and this actually gets pretty cute, doesn't it? Negative 1 minus 1 is negative 2, so I could actually rewrite this as negative 2e to the x plus 1 over x minus 1, all over x minus 1 squared. That's pretty. So the moral of that story is don't disregard your other rules. Sometimes in chain rule, you're going to do chain rule, but at the same time, you're going to be using product and quotient rule, okay? So they're all happening simultaneously, and your spidey sense really has to be sort of tuned in to which of the rules you're going to use when. You'll get a ton of practice at it, so don't worry about this. Now, let's use chain rule real quick in a clever way. You're going to start getting an appreciation for, as these rules and these tricks come filtering down, they open up a whole new experience in terms of being able to take derivatives of certain functions. We know how to take the derivative of e to the who cares, right? It's e to the who cares times the derivative of who cares. That's what we just did over here. At its simplest, the derivative, I know that d over dx of e to the x equals e to the x. Now, the question is, what is the derivative of a to the x, where a is any number greater than 0, preferably not 1, because 1 to the x is a decidedly boring thing. Now watch, I'm going to do a little bit of algebra, and then, when I'm done, I'm going to use chain rule. So, I'm going to do algebra on a to the x. Let's speak some good mathese here, shall we? A to the x, now remember your rules about exponents and logarithms and exponents. I know that a to the x can actually be written as e to the natural log of a, where e to the ln of anything is that anything, right? And then I can raise that, I can take the whole thing and raise that to the x. Really, another way to write this, think about this, is e to the ln of a to the x, right? Because this guy's just a raised to the x. Now, my rules of exponents tell me that this can be written as e to the ln of a with the x in front, either way. All right, now I'm going to leave this way. Actually, though, it's probably better if we think about it in these terms. It's easier to take a derivative, because really, as ugly as this chunk is, the natural log of a times x. Now, when I always yell at my students to put the x in front, because I'm afraid that they might think that x is actually part of the natural log argument. I don't want that to be confused. X is in front. This is actually a linear term. It's linear. This is a number times x. Last time I checked, that's a linear term. So watch. When I take the derivative of e to the x ln a, well, according to chain rule, this is just an e to the blah, right? The derivative of e to the blah is e to the blah, right? Which is just x times ln a, times d blah. Now remember, it's just a linear term, and we know that the derivative of a linear term is always just the coefficient of the x term, right? The derivative of x ln a is just ln a, right? The derivative of this guy right here is just ln a. That's kind of cool. Now, you may look at that and go, oh God, Ripley, I don't want to think about that. Well, remember, this right here, this chunk right here, is the same as this chunk, which is exactly equal to that. Guess what? we've got ourselves a new derivative that we're going to want to memorize. The derivative, bottom line, of a to the x is equal to a to the x times ln a. Now that's also true of e to the x, right? Think about this, because a can be any number. So the derivative of e to the x is equal to e to the x according to this rule, right? We're saying that this is the derivative of a to the x. The derivative of e to the x is e to the x, right, times ln of e. Well, what's the natural log of e? It's 1. So it's e to the x times 1, affectionately known as e to the x. So the far-reaching consequences of chain rule are really profound. I mean, we're going to be able to use this really, really effectively, but it's not a one-off tool. It permeates all of the rest of calculus. It's going to haunt you if you don't know it. If you struggle in the first semester of calculus, it will be because you can't remember chain rule. I always tell my students, if there's one thing that I really, truly want you, one theme that I want you to allow to sort of permeate your calculus being, God, that sounds dramatic, is know your chain rule. Know how to use it, know when to use it, etc. All right, I hope that was helpful. We'll play a bunch tomorrow, so I think we're going to spend a couple days on this, just taking derivative after derivative. All right, have a really good day, and I'll see you tomorrow.